Dear students, in today's lecture we will study about two sections. 4.6, which deals with the power and torque in synchronous generators, and 4.7, which deals with measuring synchronous generator model parameters. Power and torque in synchronous generators. Basically, the synchronous generator is a synchronous machine working as a generator which converts mechanical power into three-phase electrical power. But we also studied this in previous lectures that in generators, when mechanical power is converted to electrical power, the input power is not completely converted into output power. Whatever the source of mechanical power, it must have the basic property that its speed is almost constant. So in this diagram it can be seen that input power is converted over here into electrical power. Even after conversion there are some copper losses even after the conversion into the electrical power, and after the reduction of these copper losses the output power can be achieved in the electrical form. So the converted power is shown with dotted line over here, and the value can be seen as tau induced omega m, and which can be written as 3 EA cos gamma. So gamma is the basically angle between E voltage and I current. If you see that the real electrical output power P out, this P out is equal to under root 3 Vt IL cos theta. Similarly, the reactive power would be Q out, since we know that the reactive power is represented with Q, so it would be Q out 3 under root 3 Vt IL sin theta. Similarly, it can be, these were the inline quantities. Now in phase quantities can also be described in the form of P out and Q out. So these in phase quantities would be V phi Ia cos theta and 3V phi Ia sin theta in the case of reactive and real powers. So this is basically the phasor form of the generator, and in this there would be some calculations which we would be doing in the next few slides. Since we know that armature resistance Ra is very small with respect to X of S, so we can ignore R of A. If we assume that R of A is neglected, the phasor diagram is simplified as shown. in the figure. So there is a vertical portion BC, this portion. So this BC can be represented with this equation, or we can say that BC segment is either equal to XS IA cos theta, or it can also be written as EA sine delta. Now we will see how we have written this segment equal to these two quantities. If we see this side, we can see that this is basically a small triangle, a right angle triangle. If we suppose this is a right angle triangle, then we know that the angle over here is theta. If this is theta, then this side would be, and this diagonal is XSIA, then this side would be XSIA cos theta. Similarly, if we suppose another triangle, which is a bigger triangle, this is also a right angle triangle, and we know that this side is equal to E of A, then this vertical side would be E sine delta if this angle is delta. If we know this, we can find Ia cos theta is equal to E sine delta over x of s. We have just taken this x of s towards the right side of the equation. So this can be written as the power as described earlier. But this power would be equal to P out as well as P converted, because in this case we have said that we are not assuming RA. If we are not assuming RA, then the losses after the P is converted into electrical power, there would not be any losses, so output power would also be the same. The power produced by a synchronous generator depends upon the angle delta between V phi and E of A. So this is basically the angle between V of phi and E of A. Internal voltage and output voltage. The angle is known as torque angle. So this delta is torque angle of the machine. The generator will supply the maximum power when this delta is 90 degree. If we see the equation, if this delta is 90 degree, sine 90 would be 1, and this part would become the maximum power, which is written over here in red color. The maximum power indicated by this equation is called static stability limit. Practically, the real generators never even come close to this limit. Usually it is angle have usually they have angle of 15 to 20 degree. So up till now we have calculated three equations for P and Q. If we suppose that there are these three equations and we suppose that V phi is constant, then P out and Q out would be directly proportional to Ia cos theta, Ea sin delta and Ia sin theta. If we are seeing that the induced tau is equal to K BR cross BS, or we can write it as KBR cross B net, and by opening this cross product we can write that BR B net is sine into sine delta, where delta is the angle between BR and B net. So if we are considering no copper losses, or if we are considering no resistance as we seen in the previous case, then this P converted would be equal to P of output power. So since we know that tau induced omega m is equal to P out, so already obtained P out, which is shown in green color, can be written in terms of tau induced. The induced torque in a generator is basically, this is the same slide which we have already shown previously, and we have discussed this, and thus the mechanical and electrical power can be related as this relationship. This again shows that how the mechanical power has been converted to electrical power. So now we come to the second section, which deals with the Myring synchronous generator model parameters. So there are three main quantities in the equivalent circuit must be determined to completely describe the behavior of synchronous generator. So these three quantities are the relationship between field current and flux, and thus between field current and voltage, internal voltage. Then another quantity is the synchronous reactance X of S. The third quantity is armature resistance R of A. All these quantities can be seen in the equivalent diagram. So now if we want to determine the values of these parameters, we can use the already known open circuit and short circuit tests. By using these tests, we can find the values of these parameters. First of all, we perform the open circuit test. In this, there is no load. The generator is turned at the rated speed. The terminals are disconnected from all the loads and field current is set to 0. The field current is gradually increased in steps and the terminal voltage is measured at each step along the way. With open terminals, plot of E or Vt, this, versus If, this, can be constructed. As you can see in this diagram, the plot is called OCC or open circuit characteristic of the generator. This OCC gives the internal generated voltage of the generator for any given field current. It can be seen that it shows a linearity until a point where the Vt gets saturated. If we apply the short circuit test, we connect the load points with the short circuit wire, and this completes the equivalent circuit like this. Adjust the field current to 0 and short circuit the terminals of the generator through an ammeter. Increase the field current slowly and measure the armature current IA or the line current IL. So this IA is calculated by the Kirchhoff's current or voltage law. The rotor and stator magnetic fields tend to cancel each other, thus the net magnetic field in the machine is so small that the machine remains unsaturated and SCC is linear. So in this case, it does not reach the saturation point and it is unsaturated. And the magnetic fields for short circuit test are shown over here. Since Bs almost cancel Br, the net magnetic field B net is very small. As you can see over here, the Bs and Br cancel almost each other, so the B net is quite small in this case. The net magnetic field in the machine is quite small, thus the machine is unsaturated and SSC is linear. As we have also discussed this in previous slide, that this is unsaturated. To determine the parameters from test results from the equivalent circuit for the short circuit test, the armature current can be written as something like this. So this has been taken from this diagram, circuit diagram, and we have used the Kirchhoff's current law, and we have used the Kirchhoff's voltage law so to calculate this current, and magnitude of this current can be obtained by taking the under root square, and we can just simply ignore the resistance if we want this resistance, since this is quite small as respect to this x of s. So if we ignore this, it would simply be z of s equal to EA over IA, or so since we have ignored the R of A, since we know that R of A is quite small than x of s, so it would be equal to E of A over I of A. If E of A and I of A are known, we can easily find this reactance x of s. So to determine this x of s at a given field current, first of all we get this E of A from OCC and I of A from SCC. I of A from open circuit and short circuit characteristics, we can calculate x of s by applying this formula. So in the diagram it has been also shown that this is SCC, which is not saturated, and this is OCC, which has been saturated after some time, and this is the diagram showing the reactance of S. So in this case we can calculate these values. If we know that EA and IA, we can easily find x of s. At higher field currents, the EA taken from OCC at a given field current is not the same as E of A at some same field current under SCC. And this difference makes the resulting values of x of s only approximate. So that's the reason the values are approximate, not exactly equal. Resistance Ra, which is very small value, we can be approximately calculated by applying DC voltage to the winding while machine is stationary and measure the resulting current. The measured values of the resistance can be plugged into the impedance equation, to improve the estimate of x of s. If we put these values of R of A into this, the value obtained for x of s would be more accurate. Short circuit ratio. This is a ratio usually used in industrial terminologies. That's why this ratio is defined over here. So it can be defined the ratio of field current required for rated voltage at open circuit to the field current required for rated armature current at short circuit. So this ratio is called short circuit ratio. This is usually used in industries. This term is used in industries. Now we take a look at an example 4.1. So in this example, a synchronous generator is given with Y connected circuitry, and we have they have given some parameters with Vt at rated IF, and then IFL and IF given when a DC voltage of 10 volt given. So a current is given. So now what we have to find the values of the armature resistance and the approximate synchronous reactance in ohms that would be used in the generator model at the rated conditions. Now its solutions comes, since we know that the generator is Y connected, so the direct current in the resistance test flows through two windings. Therefore the resistance is given by 2RA V over I. So in this we calculate RA by dividing 2 on right hand side, and we find that RA is 0.2 ohm. Now we calculate EA by using the open circuit test. After finding EA, we find IA by using short circuit test. Since we know that if we know E of A and I of A, we can easily find X of S. If we already have R of A, resistance, smaller resistance, then the result of X of S would be accurate. So we also put this R of A over here in this equation, E of A and I of A. After putting these values, we can find the unknown X of S. After we know the value of X of S, we can also assume and ignore RA. Now we want to check, if we ignore this value of RA 0.2 ohm, what would be the result? If we ignore RA, the result would be 1.04 ohm. You can see the accurate answer is 1.02 ohm and the approximate answer is 1.04 ohm. So both the answers are quite acceptable and quite close to each other. So you need to solve these kind of uh, examples and numerical questions from the exercise to uh, to have a better understanding. Thank you.